Hi, hello students. We are going to discuss exercise numericals of fourth lesson, that is moving charges and magnetism. It's a straightforward numericals. Most of the numericals are very easy. If you just substitute the formula, you'll be getting the answer. Yeah, let us discuss one by one. So here I've written the first problem. Straightforward. So number of turns are given. So number of turns 100 turns, and radius is given 8 centimeter. So basically it's a circular coil which carries a current of 0.40 ampere, and they are asking magnetic field at the center. So you all know very well, so circular coil, magnetic field at center, you know the formula B is equal to mu naught I by 2r, and if that has n turns, so you just have to write mu naught ni by 2r. So that is the formula. So just I'm going to substitute. So you know mu naught value 4 pi into 10 power minus 7, and the number of turns are 100, and the current is given, which is 0.4 ampere, by 2 into radius is given 8 centimeter. So 8 into 10 power minus 2 meter. See here, most of the things will get cancelled. So I have cancelled the power. So minus 2 goes off, then 100, 10 power 2 also goes off. So 4 I cancelled with 8. So this 2 to the 4 will get cancelled with 0.4. So straightforward. So if you cancel everything, then the remaining will be pi into 10 power minus 4 Tesla. Or if you want, you can write the value of pi. So 3.14 into 10 power minus 4 Tesla. That is the answer for this problem. So moving on to the next problem. A long straight wire carries a current of 35 ampere. It's basically a long straight wire. And what is the magnitude of the magnetic field? That is B. So 20 centimeter from the wire. So I will draw. So this is the current carrying wires which carries a current of 35 ampere. And from here at a distance of 20 centimeters, so some point here, you want to find the magnetic field. See students, you know the formula for finding B of a straight wire. Finite wire formula is there, mu naught I by 4 pi r into sine phi 1 plus sine phi 2. So you know very well, for infinite the phi 1 and phi 2 will be 90 degree. So sine 90 will be 1. So mu naught I by 4 pi r into 1 plus 1. So 2 will get cancelled with 4. So mu naught I by 2 pi r. So this is the formula which I have to use for this problem. See, I have written finite wire and infinite wire. So this formula we have to use. So again, just a straightforward problem. See, I did the substitution. 4 pi into 10 power minus 7 into 35 by 2 pi. Then the distance is 20 centimeter. 20 into 10 power minus 2 meter. So 35 by 10. So 3.5 into 10 power minus 5 Tesla. So this is the magnetic field due to the long straight wire. Yeah, moving on to problem number 4.3. This is very similar to the previous problem. Only thing is it is given in a different way based on the direction. As I drew the picture, so north to south direction current is moving, and they are asking the magnitude and direction of the magnetic field east of the wire, 2.5 meter east of the wire. So first let's find the magnitude. So B is equal to, again, the same formula which you used in the previous numerical, 4 pi into 10 power minus 7 into 50 by 2 pi into 2.5 meter. So it's meter, so no need to convert. Yeah, so the magnitude, I did the calculations here. So the magnitude will be 4 into 10 power minus 6 Tesla. And if you come for the direction, so if you apply Fleming's right hand rule, right hand rule, so it will be moving upwards at this point in the direction of the eastern direction, the curlings of the finger. So if you keep your thumb from north to south, and your curlings of the finger will be coming upwards, so the direction of the magnetic field will be upwards. Yes, moving on to the next problem, which is 4.4. So horizontal overhead power line carries a current of 90 ampere in east to west direction. So current is basically going in a overhead power line east to west. So you want to find the magnitude and direction of the magnetic field below the current carrying wire. So again, the formula for B remains the same. B is equal to mu naught I by 2 pi r. So the same formula we are using for problem number 2, 3 and 4. And the way they are asking the question only differs. So here, so it's again a live problem, so you can just think. So if you keep your again your right hand thumb in the direction of the overhead, the power line cable, and you're curling, so below, so you have to move your hand down below. So you can actually while doing this problem, you can maybe in your house, you can stand looking towards west. You have to stand, and you have to keep your right hand, and if you see try to move the curling, so your curling of the finger will move towards south. So if you actually really feel, no, you can actually guess the direction very easily. Magnitude, it is simple, straightforward. Current value is 90, and 2 pi, distance 1.5. So simple steps, you will get the magnitude, that is easy. B is equal to 1.2 into 10 per minus 5 Tesla. But finding the direction is an interesting thing. So if you really feel, no, then you can, if you move your right hand looking at the west, then you can easily guess the answer. See students, in CBSE board exam, these kind of numericals you may expect, because they expect, CBSE board expects children to think. So if you apply that sum in front of you, that scene, if you just imagine, and if you apply concepts in 3 dimensions, so you can actually get the answer easily. Suppose, see, let me just ask one more thing. Suppose if the problem, if they ask above the power line, see, this is below the power line, so your curling will move towards south. See, above the power line, can you guess? Yes, your guess is correct. So above the power line, the direction of the magnetic field will be towards north. That's it. Yes, moving on to problem number 5. So we have to find the magnetic force per unit length of a current carrying wire. So which is carrying a current of 8 ampere and making an angle 30 degree to the magnetic field, and magnetic field value is also given 0.15 Tesla. So force experienced by a current carrying conductor kept in a magnetic field. You all know the formula very well. So F is equal to, or F, let me write the vector formula. F vector is equal to IL vector cross B vector, or F is equal to IL B sine theta or Bill sine theta, whichever way you can remember. And here they are asking force per unit length. So F by L is equal to IB sine theta. So I value is given, B value is given. So simple substitution, if you cancel, you will get 0.6 Newton per meter, because you are finding force per unit length. So 0.6 Newton per meter is the force per unit length which it experiences. Yes, moving on to sixth problem. Here a current carrying a 3 centimeter current carrying wire. So current carrying is 10 ampere, placed inside a solenoid perpendicular to the axis. So we know, first of all, we should know a current carrying solenoid behaves like a bar magnet. Here you should not be confused by seeing the word solenoid. Solenoid is just given, so which gives magnetic field. So you can consider it like a bar magnet. So solenoid is giving a magnetic field of 0.27 Tesla. See, I drew a solenoid, and inside the solenoid the 3 centimeter current carrying wire is kept perpendicular. So we can take theta is 90 degrees. So again the same formula which we used in the previous numerical, Bill sin theta or ILB sin theta, whatever. So 0.27 is the magnetic field and current is 10, and the length of the current carrying wire is 3 centimeters. So 3 into 10 power minus 2, and sine 90, so which is 1. That's it. So it's a simple substitution. So you'll get 8.1 into 10 power minus 2 Newton is the force experienced by the current carrying wire. Yeah, yes, students. So we have worked 6 numericals in this video. So let me put another video. So the remaining numericals I will teach you in my next video. If you have not yet subscribed our channel, you can subscribe, recommend this, or send it, forward it to your friends also. So thank you, children. All the best. Score well in the upcoming board exams. Thank you.